I've called this video tricky integrals because even though we know these actual techniques to do these different integrals, sometimes you just have to see it worked out and see the differences before you can kind of get the hang of it on your own. So the first three, if you notice, they look very similar. They all have the same denominator, x squared plus 4. But because you have different powers of x in the numerators, each of these is going to have a very different strategy. So on the first one, we start by trying to say, can we make the denominator, x squared plus 4, our u? And if we do, then the du is going to need to have a power of x. It would be 2x. We'd have to have an x to the first, which we don't. So that means a u substitution isn't going to work on this one. So then we start to look to how can we make it an inverse trig integral. And because we don't have a radical, we're going to try to make it an arctangent. And because we want to make it an arctangent, we're going to make that 4 into a 1. So we're going to factor a 4 out of the denominator, pull it all the way outside the integral. And so now that will make that x squared into x squared over 4. And then we've got the plus 1 that we're after. We look at that x squared over 4 as u squared, which means u is going to be x over 4. That's not right. That should be an x over 2. Let me bring up my eraser. So that should be an x over 2, which we'll look at as 1/2 x, which will make du be 1/2 dx. And solving for the dx, we'll get 2 du. So now our integral is going to become the 3 that we still got there, but we'll change that shortly. We're going to replace the dx by a 2 du, and now the denominator is looking like what we want, the u squared plus 1. We can cancel the 2 with part of that denominator, the 1/4, pull the 3 outside, so now that's looking like 3/2, and here is the integral we wanted. And we can hopefully recognize that as an arctangent. And our u was an x over 2 and our constant of integration. So there's our first integral. It turns out to be an arctangent. Now the second one, we try thinking, if we make that denominator our u, the whole x squared plus 4, the du is going to be 2x. And we go, oh, look at there. We do have the x that we want. The constant isn't perfect, but that we can fix. So we're going to go with a u substitution where u is that denominator, and the du will then be 2x dx, and solving for dx, we're going to get du over 2x. So our integral that has that 3x squared in the numerator, the whole denominator is going to be u, and the dx is going to get replaced by a du over 2x. So that allows us to, and I wrote that as a squared, and I'm not sure why. That should be just an x. So now we can cancel these x's, and that's what we had to account for. The extra constants, the 3 in the numerator and the 2 in the denominator, we can pull all the way outside the integral, and we get an integral, an integrand, hopefully that we recognize. That 1 over u du is going to be our logarithm. So that's going to be 3/2 times the natural log of, and our u was the x squared plus 4 and a plus c. Now, we don't really have to have the absolute values here because x squared plus 4 could never be negative, but it's not wrong to put it in there if you want to be safe. Now, the next one we look at and we say, the degree of the numerator is greater than or equal to the degree of the denominator. So that means we're going to need to long divide. So we're going to say what times x squared is 3x squared, and that's going to be a 3. We'll multiply the x squared plus 4 by the 3, making that 3x squared plus 12. We'll subtract that, so we'll get rid of the 3x squareds. 0 minus 12 is going to be a negative 12. So our integral becomes the 3, And then we have our negative 12 over x squared plus 4 dx. So the integral of 3 we can do pretty straightforward. That's just 3x. Now the next part, I'm going to go minus 12 and call that the integral of 1 over x squared plus 4 dx. So now we're very much like the very first one, the yellow one we did. We don't have an x on top, so we can't make a u substitution, so we're going to have to make this into an arctangent. So we will pull the 4 out of the denominator, which will be a 1/4. And so I'm going to reduce this in a moment, but I want you to see it. And so that'll be a 1 over. This is going to be x squared over 4 plus 1. We can cancel those. And so now we are to 3x minus 3. And we're going to say over here, the x squared over 4 is our u squared. So the u is again going to be x over 2, and the du will again be 1/2 dx, and the dx 2 du. So our integral will now become 2 du over the u squared plus 1, and we can pull that 2 all the way outside, so that's now 3x minus 6 times the integral of, and here is the integral we wanted, 1 over u squared plus 1 du is our arctangent, so our final answer is going to be 3x minus 6 arctangent of the u, which we said was x over 2 plus the constant of integration. Okay, so 3 very similar looking integrals, but very different strategies on how to do them. Let's see what else we can talk about. So our next one is a definite integral, and we look at this, and our at least initial thought is, can we make u the inside of that radical, 4 minus x squared? If we do, our du would need a power of x. That would be a negative 2x. And we look up here and we say, oh, look, there's the x we want, but we don't want that 3. So what we're going to do is split this up. So I'm going to ignore the limits for a moment here. So I'm going to call that x over the square root of 4 minus x squared. Now this one is going to have the u substitution that we've already started on. But I'm going to put over here the plus integral of 3 over the square root of 4 minus x squared. Now this integral does not have an x in the numerator, so this u substitution is not going to apply. So we're going to have to come back to this and make it into an arc sign. But let's finish the one we started here. So our u is going to be valid, so we can call this, I think what I'll do is rewrite this. So our integral is going to be x over the square root of u. And let's see, our du we said was negative 2x dx, so the dx is going to be du over a negative 2x. So we're going to get our du over a negative 2x. We can cancel the x's. We can pull that extra negative 2 that's in the denominator all the way outside as a negative 1/2. And then we can write that 1 over square root of u as u to the negative 1/2 du. So that's going to be a negative 1/2. We're going to add 1 to the exponent, makes it a positive 1/2. We'll multiply by the new reciprocal, and that's going to be 2. That will cancel, and so we're going to get negative square root of, and our u was the 4 minus x squared. Now remember, we're going to have to bring back those limits here in a minute, but let's come back and do our other integral. Since this doesn't have the x in the numerator we need, we're going to have to try to make this into an arc sign. So we're going to factor a 4 out of the radical. It's going to come outside the radical as a 2, which is still in the denominator, so that's going to come outside that integral as a 1/2. And I'm going to pull the 3 out there as well from the numerator. So I'm going to call that 3 halves. And now we have a 1 over. And since we factored that 4 out, the 4 is now a 1. And the x squared has become x squared over 4. So we're looking at that x squared over 4 as our u squared. That's going to make our u be x over 2. And we're going to look at that as a 1/2 x. So the du is going to be 1/2 dx. And the dx is going to be a 2 du. So now we have the 3 halves that we pulled outside. The dx we're going to replace with a 2 du. And our radical is now going to be the square root of 1 minus u squared. We can cancel those 2's, and so we now have 3 times the integral that we wanted, which is du over the square root of 1 minus u squared. And we know that's going to be an arc sine. And so that's going to be an arc sine of, and our u is going to be x over 2. So let's put this together. We're going to bring back our other part. So we've got our, lost my pen. Okay, let me bring it back. Okay, so we have our negative square root of 4 minus x squared, and then a plus 3 arc sine of x over 2, and we want to evaluate that from 0 to 1. So plugging in the 1 first, we're going to get 4 minus 1 squared is 3, so that's going to be a negative square root of 3, plus 3 times our arc sine of 1/2. We're going to have to come back to that. Minus, and then we're going to get, when we plug in 0, we're going to get negative square root of 4 minus 0, plus 3 times the arc sine of 0. So let's see, we've got a negative square root of 3. Now the arc sine of 1/2 means what is the angle whose sine is 1/2? And sine is 1/2 at pi over 6. So that is going to be 3 times pi over 6. And we know the square root of 2 is 2, so minus negative 2 is going to make that be a plus 2. And then the angle whose sine is 0 is 0. So that's going to be 3 times 0, which is just 0. So it looks like we're going to get 2. I'm going to bring the positive 1 in front, minus a square root of 3. And when we cancel there, it's going to be a plus pi over 2. How's that for a goofy looking answer, huh? 2 minus square root of 3 plus pi over 2. Okay, so that was a tough one because it was a combination. We had to split it up into 2 separate integrals. One we did with an ordinary u substitution, and the second one had to become an inverse trig integral. All right. Now this is a little different because of our powers of x there. Now if we think in our head that u might be 16 minus x to the 6th, then du would need to have an x to the 5th. And we don't have that x to the 5th. So that isn't going to work. Our only really good option is going to be an inverse trig integral, which it might be a little disconcerting about that x squared, but let's see how this works out. If we're going to try to make this into an inverse trig integral, because we have the number before the minus sign, we're thinking hopefully this is going to become an arcsecant. Either way, we need a 1 where that 16 is. We'll factor the 16 out of the radical. It'll come outside as a 4, which will then come all the way outside the integral as a 1/4. We're not quite sure what to do with that x squared yet, but let's proceed on faith and hope that that's going to work itself out. Now we have x to the 6th over 16. Now we need this to be our u squared. So if that is u squared, then u is going to be, now the square root of x to the 6th is x to the 3rd, and the square root of 16 is 4. So we're looking at that as a 1/4 x to the third, which is going to make du be 3/4 x to the second dx. So our dx, if we multiply by the reciprocal, is going to be a 4 over 3x squared du. You with me there? Okay, let's see where this is going. We got a 1/4, and this is going to be, we've got our x squared up here, and this is going to be, I was getting concerned. I said earlier this was going to be an arcsecant. That's not true, because the number came first. We're hoping that'll be an arcsine, and I think we're going to be on our way here. So this is going to be a square root of 1 minus, we're calling all of that u squared, and our dx is going to be a 4 over 3x squared. So this has turned out to work quite well because we're accounting for that extra power of x that we needed. The 4/3 can come out, or we can actually cancel that 4 with the 1/4. So we can pull the 1/3 out of that integral, and remarkably, we have managed to get it into something that we know how to integrate. The du over square root of 1 minus u squared is going to be an arcsine. So that is going to be in 1/3 arcsine of, and our u in this case was x cubed over 4, and then a plus c because it's not a definite integral here. Okay, so the difference here is we saw for the first time some higher power of x in our radical. Now the next one, we've not seen one quite like this before, so we would really struggle. There's actually two different ways you can do this. So I'll show method 1. So strategy 1 here is we could, if we try to make u into that whole denominator, which is kind of where we're headed, then the du, we need an e to the x. So we need to somehow create an e to the x here. And so what we can actually do is even better than just that. We can say, let's go, we already have that 1 there, so we're going to add e to the x and then subtract that e to the x so that the net change is going to be 0. You with me there? It seems kind of weird, but we just added and subtracted e to the x. So now we can split this apart. We can group these together with our first denominator integral and then separate out the second term as its own. So the first one is going to become 1 plus e to the x over 1 plus e to the x dx. And then I'm going to take that minus, and then we've got e to the x over 1 plus e to the x dx for our second integral. Well, the first one's really nice because that's really just the integral of 1, and we know that the integral of 1 is just x. The integral with respect to x is 1x. Now, the second one, we've already started our u substitution. We're going to let u be that whole denominator. So in that case, the du is going to be e to the x dx, and the dx is going to be du over e to the x. So now this second integral, if we leave that e to the x for a moment, there's our u for the denominator, and the dx will replace with du over e to the x, and that will account for that extra e to the x. This is now our minus the integral of 1 over u du, which is going to be a logarithm. So we're going to get minus the natural log of the absolute value of 1 plus e to the x plus c. And this is another one that doesn't have to have the absolute value because 1 plus e to the x will never be negative. Now, it may be tempting to try to distribute that logarithm so you can get to the e to the x and simplify, but there is no property for the log of a sum. So there's our answer. Oh, let me show you a second method. So method 2, let me do that one here. I'll go in white. So method 2 I'm going to try to squeeze in over here. So method 2 is we're going to take this original integral, and instead of adding 0, we will multiply by 1 in a carefully chosen form. So I'm going to choose whatever will make that into 1. So if I multiply that by e to the negative x, it will become 1. So now when we multiply, the numerator is now going to be e to the negative x dx. The denominator is going to be e to the negative x plus, and e to the x times e to the negative x, we add their exponents, get e to the 0, which is 1. So now we're going to say u is going to be the entire denominator, and du will be, the derivative of that is e to the u du, and there's our dx, and that will make the dx be du over negative e to the negative x. So coming this way, we're going to get here's our e to the negative x, the whole denominator we've called u, the dx we're going to replace with the du over negative e to the negative x. So these will cancel. We're going to get an extra negative sign, so that'll be a negative integral 1 over u du. Now these aren't going to look exactly the same, but they're actually equivalent. So this is going to be a negative natural log of u, which is e to the negative x plus 1, and then plus c. There we go. Kind of crazy. All right. Now the next one, these come up just often enough that they're hard to remember. So we don't have a good way of integrating tangent, which I say let u be tangent. We need a secant squared x to be the du. So what we want to do is trade in the tangent squared for something that's more integral friendly. So to figure out what to trade it in for, we revisit our favorite trig identity. That's the sine squared plus cosine squared equals 1. Now tangent squared, remember, has cosine squared in the denominator. So if we divide our favorite identity by cosine squared, we'll create a new identity that has tangents and secants. So sine squared over cosine squared is a tangent squared x. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared x. So we can solve this for tangent squared x. Remember, that's our integral that we don't know what to do with, and we can trade it in for a secant squared x minus 1, which happens to be much easier to integrate. So we replace the tangent squared with secant squared x minus 1. And we can do this because the integral of secant squared is just tangent x, and the integral of negative 1 with respect to x is x, and we throw in our constant of integration. So once we get out of that tangent squared, it becomes a pretty straightforward integral. This next one is just a tough integral. We've seen this before in different versions, and I'll try to give you as many opportunities as I can because there's just so much to this that it takes a while to wind your way through it all. The best way, not the only way, but the best way is to let the u be the entire denominator. Now the du you have to think about carefully because this is a chain rule derivative, because that square root of 3x is the quantity 3x to the 1/2. So that's going to be 1/2 times 3x to the negative 1/2 times the derivative of the inside function, 3. So I'm going to rewrite that before I solve for dx and say 3 is going to stay on top, the 2 from the 1/2 will go in the denominator, and the 3x quantity to the negative 1/2 is the square root of 3x in the denominator, and all that is multiplying dx. So that means when we solve for dx, we multiply by the reciprocal, which will be a 2 over square root of 3x in the numerator and a 3 in the denominator times the du. Whew. Okay, well, this is only the beginning. We'll have that 2 in the numerator. We're calling the entire denominator u, and the dx is going to get replaced by 2 square root of 3x all over 3 du. Now, the constant stuff is not a big issue. We can pull all that out. The 2 times 2 is 4 over 3, so that's going to become 4/3 outside the integral, but we have a bigger issue with that square root of 3x because we're trying to get this to be an integral of u with du in it, and we still have this lingering square root of 3x. So we revisit our substitution, where we said u is 1 plus the square root of 3x, and see that if we subtract that 1 to the other side, we can say that the square root of 3x is u minus 1, and that's what we're going to do. So now we have our 4/3, and now this becomes u minus 1 all over u du. And this is not a real obvious answer either, but we're going to split this fraction u minus 1 over u into two different fractions. So that's going to be u over u minus 1 over u, still all times du. So, rewriting that down here, u over u is 1, but remember that's with respect to u, and then I'm going to go minus and bring that 4/3 with it, times 1 over u du. So, we're going to get the integral of 1 with respect to u is not x, it's u, so that's going to be 4/3 u minus 4/3 times the natural log of the absolute value of u. And so then we can finally go back to our x's, and our u was 1 plus square root of 3x, and then we got a minus 4/3 natural log, and this is another one that doesn't have to have the absolute value in it, but it's not wrong if it does. Square root of 3x can never be negative, so 1 plus square root of 3x can never be negative. And all of that is our answer. That is just one tough integral. Okay, now here is another one that's going to take some creativity. So we're going to say, let's try letting u be the entire denominator. So that would be x squared minus 2x plus 5. Du then would be a 2x minus 2 dx. And we look up there in the numerator and we see, well, we got the right power of x, but we don't have that minus 2. Well, let's see. Let's see if we can see where this leads us a little bit more. If we solve for dx, we're going to get du over 2x minus 2. Now, we can think of that as du over, and if we factor that 2 out, it's going to be an x minus 1. So really the bare essentials of what we need in that numerator is not an x, but an x minus 1. So I'm going to just put that negative 1 and then turn right back around and add it so that I'm really adding 0. Now this will then satisfy what we need for our u substitution, but I'm going to have to separate this into two separate integrals. So the one integral that we've been working on here is going to be our x minus 1. Then I'm going to move the plus 1 over that same denominator, x squared minus 2x plus 5, to be its own integral altogether. Now the first one is going to work great with this u substitution that we've been working on. The denominator is going to be u. Our dx, we said, is going to be du over 2 times the x minus 1, which is great because those x minus 1s will cancel. That extra 2 we can pull outside the integral as 1/2, and our integral is one that we know and can do. That is going to be 1/2 times the natural log of the absolute value of u, which we said was x squared minus 2x plus 5. Now, we're going to park that for a minute because now we have a whole nother integral that we're going to have to do, and that's going to be this one right here. Now this, we can't do the u substitution that we just did because we don't have any x's on top. So this is going to have to become an inverse trig integral. Since we don't have any radicals, it's going to need to be an arctangent, and because an arctangent is going to be 1 over u squared plus 1, we need to complete the square in order to get that u squared. So I'm going to push that plus 5 out. Let me scoot it over a little bit more. And then we're going to take half the middle term, square it, and add in 1, and then subtract it back off, so we're adding in 0. So now this part right here is going to be a perfect square. So that's going to become 1 over, and that's going to be an x minus 1 squared. The negative 1 plus 5 is 4, and dx. Now we're on our way to getting a u squared plus 1. We want to make a 1 where that 4 is, so we'll factor a 4, out of the denominator and all the way outside the integral. That is going to make that x minus 1 squared into x minus 1 squared over 4, but we've got the 1 that we wanted. Now we see that x minus 1 squared over 4 as u squared, so our u is going to be x minus 1 over 2. We see the x minus 1 over 2 as a 1/2 minus 1/2 x minus a half, so the derivative of 1/2 x will just be 1/2 dx, and that means the dx is going to be 2 du. We're getting there. So now we have a 1/4, and the dx we're going to replace by a 2 du. That x minus 1 squared over 4 is now u squared plus 1. We can cancel that 2 with part of that 1/4, and we have the integral that we can do. And that is our arctangent, and our u is going to be, what did we say? X minus 1 all over 2. So putting the whole thing together, we have our 1/2 natural log of x squared, absolute value of x squared minus 2x plus 5, plus 1/2 arctangent of x minus 1 all over 2, and our plus c constant of integration. That is a tough integral, but one that we'll get the hang of eventually. All right, now this one is just tough for different reasons. There's actually 2 ways you can do this, neither one of which is very hard. One is if you can guess the right u substitution to make. The second one is if you don't guess right the first time, you can do it with 2 substitutions. So I'll show you both ways here. If you are fortunate enough to be able to tell or guess that the best choice for a u is going to be natural log of sine of x, then du is going to be this chain rule derivative. Remember, the derivative of natural log of u is going to be 1 over u times du, and the derivative of sine x is cosine x. Well, we know that that's really just cotangent of x dx. Or if we like, because we're going to try to solve for dx, we can multiply by that reciprocal, which would be a sine x over cosine x times the du, or that's otherwise known as a tangent of x times du. So that is going to be a cotangent of x. That was our original. Still is there, I'm sorry, that's just there. And the natural log of sine of x we said was u, and the dx we're going to call a tangent of x du. Now, if we go to sines and cosines, maybe we can see this a little more clearly. the cotangent is cosine over sine, and the tangent is sine over cosine. And so you can see that they are going to completely cancel each other out, and the integral becomes a pretty straightforward u du, which is going to be 1/2 u squared plus c, and so we can go back to our u, which remember was that crazy natural log of sine of x plus c. So there's one way, and that's the most efficient way, but pretty tough to see that first u substitution. Now, it wouldn't be unreasonable to try, here's the second way. You could say u is maybe sine x, because that looks like it's an inside function. So du would be cosine x dx, so the dx would be a du over the cosine of x. So in this strategy, we've got that cotangent of x, we've got the natural log of u, and the dx we'll replace with du over cosine of x. So if we do that, then let's see what we can do. We could say that that cotangent is cosine x over sine x. We've got the natural log of u, and then we've got this du over a cosine of x. So here we can cancel these cosine of x's, and now we're looking at this integral of, I'm going to call it natural log of u over the sine of x, and we've got a du, and we're going, what are we going to do with that sine x? And then we go, wait, that's our u. So this integral is actually the natural log of u over u du. Now, if you think about that, we can do this. Now I'm going to make another substitution, and I'm going to let it be, now I've already used u, so I'm going to pick some new unused variable. So I'm going to say w is going to be the natural log of u. Then dw is going to be 1 over u du, and solving for the du, it's going to be u dw. So that is going to make our integral, the natural log of u is now going to be w. I'm going to leave that u for a moment, but the du will get replaced by u times dw. And so we can cancel those u's, and at long last, the integral becomes something that we can do. So that will be 1/2 w squared, and then I'm going to go back to, from the w's to the u's. That was a natural log of u squared, and then we'll finally go back to our u substitution, which we said was sine of x, and so that is going to be 1/2 the natural log squared, and I guess I should say absolute value of sine x plus c, and hopefully, except I may have forgotten the absolute value sign earlier, yep, so I'm going to reinsert that. That should really have been an absolute value of sine x. And we get to the same thing. Crazy, crazy, crazy. Well, there are some tricky integrals.